Hello guys, turn your cameras on so I may see your honest, hardworking faces. Yes. I only see how many faces do I see? 1, 2. Oh, just what? 1, 2, 3, 4, 5 guys. What about the rest of you? Are you here? Turn on your faces. Good. Good. Wonderful. Don't worry, it's a good training for you. Once you learn how to do other things, but yet pretend that you are thinking about the material that I'm teaching. Yes, I am good at it, I think. I have to attend seminars just like you do, right? Some of them are 2 hours long, right? And very often I do this face. And what I actually do is right at the side, I have some other book that I'm doing. Maybe I'm reading something or doing practice exams. It's something that has nothing to do with any exams that I'm taking. All right. So guys, I'm very happy that you are all intimidated and turn your cameras on. That's very good. Now I can at least recognize some of you. And I'm still grading your exam. It will take me a snail's pace. And I do that also to not be too enraged. As you see, I mean, I just grade a few questions right away. I begin to boil. So I try to keep it at distance so that I am very nice and calm. You all received my message, and I hope in the future you will consider to not post those questions or do group work, especially when that happens to be a wrong solution. And when it's a wrong solution, it's easier to feel off about it. All right, so what have we spoken about? So we began doing binomial random variables. And you remember what it means, guys. We have n trials, and the probability of each trial is independently a success with probability p. And so the probability that we get exactly k successes is n choose k, p to the k, 1 minus p to the n minus k. I hope you remember why, right? You see where the n choose k comes from. That is over all the possible choices of k successes that you can select. Good. And we solved already a few questions regarding this probability. Some of them were easy. One of them was a bit more complicated. Actually, 2 of them were a bit more complicated, especially the very last question with which we finished. And about the electronic device, you remember that, right? So we wanted to figure out when is it worth introducing more components than fewer components. And my example is my analogy, which is probably not the correct analogy. I'm not sure what is the correct one, but an airplane with 1 propeller as opposed to an airplane with 2 propellers, right? If I make the propeller, right, how many propellers do you want to have on your airplane if I am the one designing them? And I know nothing about propellers. So the probability it fails, if I build it, is very high. Do you want more propellers or do you want fewer propellers? And that's the question. 2 rather than 1, right? So you imagine, right? Maybe, right? So sometimes, I mean, the system is tricky. That's the thing. It's not that each propeller keeps you on. There is another condition, is that you want more than half of them to be functional. So you need, in this question, an odd many devices, each functions independently, and you want more than half to function, right? For this device to continue working. So we solved this question, and what we did, we realized, you can try to read it through or maybe think about it on your own, see if you can come up with a solution. So by carrying out this comparison, we realized that when we start here, we realized that that the probability that less than n propellers fail in a system that has 2n plus 1 propellers is higher than the probability that n minus 1 propellers fail in a system that needs that has 2n minus 1 propellers, as long as we see that the answer is near 1/2, right? So you want the probability of failure to be less than 1/2 for this type of system. Yes. So that means that when the device has a more than 50% chance of working, you want more of this device as much as possible, right? The more you have in the system, the more likely it will work. All right, so then we can consider now properties of binomial random variables, and we need to figure out what's the expected value and variance for the binomial random variables. So I will probably maybe skip this way of doing it, although it's in my notes. You can derive expected value without using properties of expectation, right? I never recommend to ignore those properties because very often it's more complicated without them. As in this case, you see I calculated the expected value of the kth moment, and here you have both expected value and variance. So I will skip the A version of doing it with your permission, and we will do it using properties of expectation. So we have that the total number of successes is the sum of the random variables x1, x2, all the way to xn, with each of them contributing a 1 if the corresponding trial is a success, right? So x1 contributes a 1 if the trial 1 is a success. Yes? So I can break it apart like this. Now, what is the expected value of x? Even if the variables were not independent, it would be expected value x1 plus expected value x2, and so on and so forth, right? Now, each of them is identically distributed. Can you see that? So each of the expected values, x1 through xn, only looks at the particular entry in the string of trials. So x1 only looks at the first trial, x2 looks at the second trial, and so on. So expected value of x1 is equal to p. Do you agree? Because the first trial will just be with probability p successful, and expected value of x2 is the same, right? It's 1 multiplied by the probability plus 0 times the probability of failure, but we don't even need to consider that because 0 multiplies the probability of failure, and the expected value is just 1 multiplied by probability of success. So you can see that each of them contributes at p, and we have p plus p plus p, we have np. Yes, so the expected value of x is the number of total trials multiplied by probability of success of each. Good. So for instance, if I have 10 trials and the probability of success is 1/2, I expect on average to have 5 successes. Yes. If I have 30 trials and the probability of success is 1/3, I expect on average 10 successes out of 30, right? Probability success is 1/3. I do it 30 times. I am expecting 10 of those trials to be successful. Good. Now, how do I calculate the variance? Also, the same way as you can just say variance of x is variance of x1 plus variance of x2 plus variance of xn. Remember, I cannot do that same linearity for variance unless covariance is 0. You remember that, guys? So variance of the sum is not the sum of the variances in general. It is only true when the covariance is 0. But here we have independent trials, so one does not influence the other. When trials are independent, as we saw in the calculation of covariance, covariance happens to be 0. You with me, guys, still? You remember covariance? I hope so, guys. Yes. So in variances, again, are all the same. We have n times variance of x1. What's variance of x1? Yes, guys, I'm either having a stroke or some of you are disappearing from this from my field of vision, you know. So it's n multiplied by variance of x1. And what is that? So let's say, so are all of the xi variances the same? Then absolutely, all of the xi variances are the same. Do you see why, guys? Because really each trial is identical. They're twins. Doesn't matter if it's first trial or second trial. They don't really correspond, so they're identical. Yes. And so what do we see? We see that a variance, let's say, of x1 is the expected value of x1 squared minus the square of the expected value of x1. We calculated those before. Now, the expected value of x1 squared is just 1 squared when the trial is successful, and 0 squared when it's not, right? So it's really just 1 squared times the probability of success, which is p. So expected value of x1 squared all happens to be the same as expected value of x1. In fact, all powers happen to be the same. Do you agree? So expected value of x1, x2, x3, x7 are the same, right? They're all p. You all see that, guys? They are all equal to p because it's an indicator on the variable. It's 1 to the power of 2 in this case times probability p. But the second part we square, so it's p minus p squared, so it's p times 1 minus p if I factor it. And so the variance of x is just n copies of this exact same expression, and we get n times p times 1 minus p. I would like you to contrast it with the with a that I skipped. You can see that you can accomplish it without without using those properties, but it ends up being much less pleasant and long. Yes. So what next? Next, we want to observe how the distribution behaves. When do you expect the number of successes to be most frequent? What number of successes do you expect to be more frequent? Right. So that's the next distribution, and it tells us that the probability of having k successes is bigger than or equal to the probability of having k minus 1 successes if what happens. Yes. So then you can just simply see when the probabilities grow. So what happens? So if I take the quotient probability of x equal to k over probability x equal to k minus 1, here are the probabilities. I take the quotient, I simplify it, and I get this expression. This is just algebra, you can follow. Yes, just when you do this algebra, you get this expression. Now, once you move things around, you see I take k, I multiply in the denominator, I take p, I multiply the numerator, and this is the numerator and this is the denominator. I just move them apart, right? I multiply 1 by k times 1 minus p, and I simplify it, and you can see I can cross out k minus p here and here, and I'm left with np plus p bigger than or equal to k, and that's the same as n plus 1 times p bigger than or equal to k. Which means what? Which means that the probability of having more successes keeps increasing until k reaches to the biggest integer that is equal to or below n plus 1 times p. Yes? So what does it mean, for instance? So if you take a very simple example, if you take probability of success 5 and 10 trials, right? So 0. So what do you then have? Then you have n plus 1 is 11 times 1/2. It's 5.5. Yes. So as long as the integer is below 1.5, the probability of success will increase. So for instance, 0 successes, 0 is smaller than, you can see 1 is smaller than 5.5, which means having 1 success has bigger probability than having 0 successes. Yes. 2 is smaller than 5.5, which means having 2 successes is bigger than having 1 success. The probability is bigger. Yes. And I can go onward. So 3 is bigger. Probability of having 3 successes is going to be bigger than probability of having 2 successes. Do you see why? Because 3 is still smaller than 5.5. And when do I stop? At 5, right? So so 5 is the last time I climb, right? So 5 successes is going to be bigger than 4 successes, but 6 successes is already going to be less likely than 5 successes. That's what this calculation is telling us. You understand? And it's true for all other probabilities and numbers. You can just figure what's the most likely arrangement of successes. How many successes are you most likely to see? And that depends clearly on the probability of success and, of course, on how many trials we have. The more trials, the more likely a success to be seen, right? And yes, makes sense, yes? And this can also be used as a recursive procedure. If I calculate this probability, I can figure out the next probability. So I'm not going to go there, but you know, the anxious K is very costly, but you can design, you can create a recursive procedure to calculate next probability from previous probability by multiplying it by rather few numbers. Yes. So you can see, for instance, yes, you can see that the ratio of pxk divided by that is equal to this number. Yes, so all I have to do to calculate p equals to k is just take this number and multiply by what you have on the denominator, right? Assuming I figured it in the previous step. That's what I mean by recursive calculation. Yes, so you can use this procedure, and for, especially for computers, but also for yourself. You don't really need it. I mean, you have a calculator. You know, you don't feel the burden. But when you, if you had to calculate such things, you would probably use recursion. Right? I mean, it's not easy to calculate this probability by itself. Maybe it's easier to take this probability and multiply by this number. So you can go with 0, and once you know 0, you can figure out what 1 is because of 0. You can figure out what is 2 is because of 1, you know, right? And so on and so forth. And by just multiplying by this number, which is relatively easier than just calculating it from scratch. All right, and now we talk about hypergeometric random variables. And I cannot ever remember when you would ask me even after this lesson, what is hypergeometric? And I would say, what? I never remember the name. I do not know why it's called hypergeometric, but I also do not know why geometric series are called geometric, really, right? Once you know the reason, then maybe you remember it better. But what is this thing doing? So it's very similar. I call it the distribution. It's very similar to binomial, except that sampling is done without replacement. Okay, so that each trial is not independent of the previous one. So here is the situation. So imagine we have an urn in which we have W white and B black balls, and we want to draw a sample of N balls where N is bigger than the total or equal to it at most, right? And we want to know how many white balls are in the sample. Make sense? So it's done without replacement. Once a ball is removed, it's never placed back in. You can also withdraw them simultaneously. It's up to you how you do that, right? But either simultaneously or sequentially ends up a similar thing. But okay, so what is the distribution here? So first, we describe the distribution as okay. It's very similar to binomial in some sense, where you have n trials, and the probability of the trial success is W over W plus B. Except once I withdraw a white ball, then I have fewer white balls to withdraw, and the probability of doing it again is lower. So it's not exactly the same distribution. Yes. Now, what is the probability of withdrawing exactly K white balls? Well, that is the same as first of all, I can withdraw any, my sample consists of any N balls out of W plus B. Do you agree? I mean, if I do it sequentially or however I do it, it looks by symmetry. It seems by symmetry that I can equally likely produce any type of sample of size N, which means any of W plus B balls are equally likely to be selected. That's my denominator. W plus B choose N. I hope you know the Kafka protocol, so I don't need to write it. You see how I think of it, right? This is all universes. That means this represents all possible samples where I regard each ball as individual, as numbered 1 through W, then then W plus 1, W plus 2, all the way to W plus B, and those are the black balls. Yes, and then out of the white balls, I have to, if I select K white balls, which individual white balls did I select? So it's W choose K, and times which individual black balls I selected. B choose N minus K. Together they make a sample of size N. Yes, and of course we can observe that the summation equals to 1. The sum of the probabilities always equals to 1 if you correctly describe the random variable, because the random variable just relabels individual outcomes of sample space, right? And the sample space, when you simulate a probability, every outcome must be included in the sample space. So probability of sample space is 1. You agree? So we can calculate, for instance, suppose that in general, I can get at most minimum of W and N white balls, right? How big is the sample? How many white balls I have? At most I can get the minimum of W plus W and N. So if N, the sample, is smaller than W, then I can get up to N white balls. In other words, all balls in my sample can be white. Yes? Now, this summation is what, guys? If I sum probability x equal to k, I get all of them have the same denominator, W plus B choose N, but we have a different number of white balls, right? So we have white 0 all the way to N, right? So, and what is this number? What is this summation, guys? This summation is the same as taking, because here what do? I partition W plus B choose N into how many white balls I have. I have 0 white balls, 1 white ball, all the way to N white balls, right? So that's just like, remember, we did such combinatorial identities before. So it's just W plus B choose N. That's what the numerator is equal to. Do you see it? I hope you do, right? It's like we have boys and girls, or basically 2 categories. If I have 2 categories and I choose N objects out of those categories, then I can write it based on the events where I choose 0 of first category and everything from the second, or 1 from first category and everything minus 1 from the second, and onwards, right? So this equals to the number on the numerator, and together they have a ratio equal to 1. And here is a very simple example of hypergeometric random variable. Again, I can never remember. I mean, no matter how many times I hear this word, I never remember what is hypergeometric. Yes, unless some of you are going to figure out why it's called hypergeometric. A forest, I would call it, again, my name for it is looks like binomial, but not random variable, right? So what it is, a forest has N elk. Today, M of the elk are captured, tagged, and released, which is, by the way, what I did as an amateur hunter professor. I catch elk that cheat on my exams, I tag them, and I release them. And that happened in 2017, but they didn't listen to me, right? I just caught them, but they don't get smarter from that because they are elk. Yes, I'm humane. I mean, I figure the education is a lie anyhow, so, you know, why bother? So here was what happens. So at a later date, N elk are randomly captured. Assume that each of the elk of the N elk is still equally likely to be captured. What is the probability that K of the original elk are recaptured? So very simply, what does it mean? We have a bunch of elk that wear an earring, right? They were tagged. So there is this earring, they are fashionable. And the earring says cheater, right? So, so you have how many of them? You have M of them have this earring. And now what's the probability I'll capture K of them? Well, out of M, I pick K. And out of the remaining one, you see N minus M are those that were not previously captured. I capture N minus K. Yes. So this is very easy. Yes. Now, another one, a 5-card hand is drawn at random. The number of aces in the hand is either 0 or 1 or 4. What's the probability that you have K? So you see we have cards. A card is labeled as either ace or not ace. Yes, and I pick 5 of them. So there are 52 cards. Exactly 4 are labeled as ace. What's the probability of having K aces? It's 4 choose K, 48 choose 5 minus K. You agree? Very simple. So that's an example of hypergeometric random variables. You write it in some books. You write it as here is the number of. This means the number of objects with the tag that you're searching for. This is number of objects that have a tag that you don't want, and this is the sample size. You see, so tag that you want, tag that you don't want. And the last one is sample size. So in the original example, white balls, black balls, sample size. Good. Now, this is an interesting theorem. It's a bit difficult, but I hope I will be able to explain it to you well. I will try. So there is another way of writing that probability that looks less intuitive. And what this is saying is that the two hypergeometric random variables that have distributions like this. So W, the things that you want, the things that you don't want, sample size, and this way of writing it have identical distribution. Now, what do I mean by that? What I mean by that is the following. So imagine that the way the balls, we have those balls that you sample. You can imagine two ways of what happens to them. Imagine that they are being produced in a factory, and in the factory, they are labeled with two tags. One tag is sampled, and the other tag is white or black. Okay, so you just, the ball has, you can imagine the color, but you can also imagine that there is a tag. It says white, sampled, or not white, sampled, or you know, or not white, not sampled. You understand, right? It just has two tags. Two things are written on each ball. So one way is to imagine that the tags are pre-assigned. So first, you have all the W plus B balls, and the tag white and black are assigned, right? Not randomly. They just kind of, let's say, first you have this pass dispenser, or you have this conveyor belt of W plus B balls, and the first W of them are stamped by the machine with the letter W, right? And the remaining ones are stamped with the letter B, or colored, or whatever you like to think of it, right? And then what happens, the sampling is done randomly. So the stamp where you have the S stamp or not S stamp is random. It's not this, right? And then what happens is the probability that you have K is W choose K, B choose N minus K, W plus B choose N. The original way of doing it, right? The original way of doing it is that the colors are determined ahead of time, and sampling is not determined ahead of time. Sampling is done later. Sampling is the randomness, right? Now, you can think of this in reverse. You can imagine that sampling is done non-randomly. So the balls have no label of white or black. You first sample them, which means you just take the first N balls, right? Take the first N balls, and then randomly all the balls, the balls that you sampled and the balls you did not sample, they are assigned randomly the tag white. Some of them receive the tag of being a white ball. Can you imagine that, guys? So what happens then? Then the probability that you get exactly K white balls means that out of the N balls that you're holding, exactly K of them will turn white. And out of the balls that you're not holding W plus B minus N balls. Out of those, W minus K will turn white. The remaining ones obviously are black, right? So once I mention one category, I know what happened to the other category. And here, in general, out of all the balls, just some W of them will turn white. You see what I'm doing here, guys? Here I am. There is a symmetry of tag. The tags make it symmetric distribution. It doesn't matter if the tag is W or the tag is S. Do you agree? That's the symmetry. But in your mind, you think your sampling is random. But really, if you realize that it's the same as assigning two different tags, yes. So by symmetry, it doesn't matter which tag you assign randomly. Right? So when you randomly pick a sample, that means that you assigned the white tag beforehand and then randomly assign the sample tag. Whereas in the second calculation, we decided we are going to assign the sample tag non-randomly, but the white tag we assign randomly. Are you following, guys? It's very difficult. So I'm not sure if you are. I think it's difficult, at least. I don't think I right away realized it. But how about you? Do you have questions? All right. I hope then that means looks okay. So my explanation, all right? Understand? Okay. All right, guys. We'll see later. All right, so here let's begin looking at properties of hypergeometric random variables. So of course we want to calculate expected value, and expected value happens to be just the same as it was for binomial. You agree? So the probability of success for any particular trial is number of whites divided by total number. So if x is equal to x1 plus x2 all the way to xn, that's the sample size, right? Each of them is adding a 1 if that trial number is a success. Now, if I focus on any x, if I focus, let's say, on x2, x2 is equally likely to be any ball. Do you agree? So the second trial, any equally likely in general to be without information of what has happened before. It's equally likely to be ball 1 through ball W plus B. And exactly W of them are white. So the expected value of x1 or x2 or any of them is W over W plus B. And so the expected value of x is n times that. Good? So notice W over W plus B is that P from binomial. Same thing. Now, where you're not going to see the same expected value is when you calculate variance. Because variance of the sum is not sum of variances. Do you agree? It is not the same situation because variance requires independence for this to happen. Expected value or first moment does not require independence. So variance, what is variance here? It's variance of x1 through xn, and that's the summation of all the variances plus the summation of all the covariances. Yes? Now, because the random variables are essentially all the x's are identical, so this summation can be replaced by n multiplied by variance of x1. And how many covariances do we have here? Think about it. We match every x from basically covariance is like we have two parentheses. We have x1 plus xn here and x1 plus xn here. And we have a match for each x from the left parenthesis with each x in the right parenthesis. And for each of them, we calculate covariance. That's what this summation means, yes? So every xk meets every xj from the second parenthesis. This is left parenthesis, this is right parenthesis, and they meet once, right? And I can simplify it further by just seeing when let's say x1 meets with x2. So once it's x1 is here and x2 is here, and once it's reverse. Yes? So in general, you would have n choose 2 multiplied by 2, and choose 2 for 2 combinations. First parenthesis, second parenthesis, multiplied by 2 because it could be like this. So we can simplify it as n times n minus 1 covariance x1, x2. Are you okay with the simplification? I haven't skipped too much. You see why this calculation is what I wrote. Yes, guys, don't hesitate if somehow something is unclear or you want to be elucidated, then just ask me a question, yes? Very often people make smart faces. I know how it feels. I took linear algebra a long time ago, and I thought everyone was just understanding it perfectly, and only I had questions. And it turned out that it's not true, right? Not true in the least. So people have very smart faces, but even sheep can sometimes have very smart faces. So, you know, it doesn't mean anything. So always ask questions. Be brave. So yes, so then how do we calculate those values? First, let's calculate the expected value of x1 squared. We need it for the variance, yes? Now, that's the same thing as w over w plus b, same thing as the expected value of x1 without the square, yes? Because it's an indicator variable. Now, what's variance? It's then the expected value of x1 squared minus the square of this number. And when I simplify it, I get this expression. So far, so good. What about covariance? I now need to figure out covariance. So I need the expected value of x1 times x2. That means that both of them have to be 1. x1 is 1 and x2 is 1. So how many possibilities are there combined? So for x1, the probability of being 1 is w over w plus b. And then given that x1 is 1, x2 has w minus 1 white balls to deal with and a sample size of w plus b minus 1 to deal with. So it's this product. It's a conditional probability, right? So it's the same as the probability that x1 is equal to 1 times the probability that x2 equals to 1 given that x1 is equal to 1. And you get this number. Are you following me, guys? That the expected value of an indicator variable or product of indicators is just, it's directly related to probability. Yes, because it's probability times 1. So yeah, so it's just probability. Yes, you all see that, guys? So what is this? This is just the probability x1 and is equal to 1 and x2 is equal to 1 times 1 plus 0 times the probability they don't. But that means this means the probability where this is 1 and this is 1. So the probability that x1 is 1 is this number. The probability that x2 is 1 given that x1 is 1 is this number. You see it? And I multiply it in the product. I hope I explained it well and you would remember it afterwards. Yes, guys? So what is covariance then? Covariance of x1 and x2 is simply this number we obtained minus the expected value of x1 times the expected value of x2. They are the same. So it's this number squared. And then I just simplify it and I get this thing. Yes, just you can multiply it and you'll simplify it. And you get this thing. And then what is variance? Variance is the variance x1 multiplied by n and covariance multiplied by n minus 1, which if you simplify, you get this number. It's afterwards just algebra. Good? So try it on your own, guys. Afterwards, you close the book, you don't look into it and see that you can derive this. All right, so then we're here, I think. All right, so then we want to see some connections between binomial and hypergeometric, explore some of them a bit more. So this is pretty interesting. It's called Fisher exact test. And the idea is to see whether or not a null hypothesis is true between, let's say, two categories. So for instance, maybe you have the hypothesis that a disease affects women and men equally likely. That's your null hypothesis, let's say. Right? Maybe you think it's not true, maybe you think it is true, but you can use this test to consider it. Suppose that what you have is this table, right? So you have a total of n plus m people. You have n women and m men. And you look at this disease and you see that k women have the disease and r minus k men have the disease for a total of diseased people r. Yes, and then no disease is the same thing, right? You understand? You break n plus m into diseased, not diseased, and then each category m and n you break into the same thing. Good. So if the null hypothesis is true and the probability that women and men are afflicted is the same, then P1 and P2, P1 is the woman probability and P2 is the man probability, they are the same. It's equal to P. And then if this is true, then the way we judge is, I mean, is this table likely? If this is true that they are the same, is this table likely? Right? So let's see what would be the probability of having this table. So the probability in general that K women are sick, given that the total number of sick people is R, is the same as the probability probability that K men are sick, K women are sick, R minus K men are sick, divided by the probability that the total number of sick people is R. X plus Y is number women, number men. Yes? Now, what is that distribution? Well, let's look at it. So this is the probability, it's the same as probability K men are sick times the probability, K women are sick times the probability R minus K women are sick, because we are presuming it's independent, right? There's also independence between the men being sick and the women being sick. Right? In other words, if I know a man is sick, it doesn't affect my knowledge if a woman is sick. So what do you get? You have to always be tremendously careful in statistics. You know that, guys. I mean, you might make an assumption at some point, and this assumption is just you made it many times, and it could be that the assumption is absolutely wrong, and then the calculation and everything you do and the presentation is absolutely wrong. That's why statistics is tremendously difficult and tremendously deceptive. It's very, very difficult to control a lot of things. So what do you have here? Probability is then what? This is the probability that you have this many women sick, right? So each woman independently becomes sick and each man independently becomes sick. That's the idea here, right? So n choose k, p to the k, 1 minus p, n minus k. Yes, and that's how many women we have. And this is the binomial distribution for them to become sick. Times this is because this means K women became sick and this many men became sick. Yes, and we have this same calculation for men. And the bottom is what? That R people became sick is just which of the R people became sick, also binomial. N plus M choose R. Right? And then when you simplify it, you see that all the probability, this unknown probability P disappears. You can erase it. And what you are left with is the hypergeometric. N choose K, M choose R minus K divided by N plus M choose R. Are you with me, guys? And note the assumptions I made. I made many difficult and very possibly untrue assumptions. So even applying this test is complicated. I assumed that each person gets sick independently of another. That's not true of all diseases. Do you agree? I mean, you would imagine that if many people are sick and they are sick with something infectious, then it's not true that each of them gets sick independently of another, right? If I see somebody get sick, maybe that affects it. Who knows? It's very complicated to judge it. But if it's some other disease, maybe it's poisoning or I don't know what, you can have it, right? Something that somehow is independent, then the assumption might be still true. So this is what we have gotten. This is the ratio, and this is the probability that we see this particular table. Right? That's the probability we can see this table. Let me show you with a concrete example of how that might work. Yes. So suppose that I do a study and I try to find how frequent is a particular disease, and I see that, well, I had a total of 24 study objects, and out of them 10 got sick. Yes. Now, out of those 10, 9 are women and 1 is a man. Yes. Now, what is the likelihood of seeing that? So you see, given that I have 10 sick people, what's the probability that if men and women are equally likely to catch it, what's the probability that I have this, right? Have this type of distribution. I began with 24 people, 10 of them were sick and not, right? So what do we calculate? We calculate probability that X equal to 9, given that the total X plus Y, total people that got sick is 10. Yeah. What do we get? We get, we had, how many men and women we have? The same. So we have 12 choose 9 women that were sick times 12 choose 1 men that got sick divided by 24 choose 10. That's the probability that you picked 10 people out of 24 that are sick. Okay. And this number, when you simplify, is about 1 in 1,000. Yes. So that means that if men and women are equally likely to catch this illness, then seeing this type of distribution of sick people is 1 out of 1,000. And then, of course, is it low or is it acceptable? That depends on the criteria, right? So that's when you decide when you reject the null hypothesis. When does it appear that it's too unlikely? Yes. So if it were 1 in a million, you would be much less convinced that the probability of men and women being sick with this is equally likely, right? So when such a thing it can be applied, for instance, I don't know, maybe breast cancer, right? Maybe some things that are much more, you can kind of imagine independence. I'm not sure if infectious diseases are good for this. You would have to really think and be very careful. Yes, but you can see here, just if you have 2 categories and you assume that the probability that each person has it independently is probability P, regardless of the category. And then if that's true, is it likely that you will see this result? And you can see here it's 1 in 1,000. If this number is smaller, then you believe, well, it's much more possible that there is something wrong in my assumptions, that it's equally likely. And that's when I reject the null hypothesis. Make sense? It's like the same thing that people are pre-built to think. I mean, if I ask you this, guys, imagine I took a fair coin. This is a simple question, right? Let's see what you would answer. Let's see if you still are awake this way. I take a fair coin and I toss this coin 1 million times, right? And all the times I tossed it, I got heads, 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 right? Always heads. It's a fair coin. What's the probability that I will get heads on the 1,000,001st trial? Please write. You understood what I'm saying, right, guys? I picked a fair coin and I tossed it 1 million times, and every single time I got heads. What's the probability I'll get heads again on the 1,000,001st trial? Okay, so I see a few answers right now. Some people say 1/2. One person says 1, right? So why not everyone? Why don't I see 20 responses, guys? And the others, guys, what's up with you? All right. Now, you see, why did I ask this question? So the answer is clearly 1/2, because I said it's a fair coin, right? If it's a fair coin, then each time you toss it, the probability is 1/2. Now, why would anybody hesitate? If you ask it on the street, most people would say 1. And some people here said 1, and others, of course, just decided they don't want to risk it with me, right? Why would you say 1, guys? Because you don't believe me that this is a fair coin. That's why you say 1. And that's a very correct reason not to believe that it's a fair coin. If it were a fair coin, I am not going to witness 1 million successes. It's not going to be possible. Yet I will never witness. I mean, the probability of witnessing 1 million successes, right, is 1/2 to the power of a million, guys. I am not going to ever in my life and possibly in the existence of the universe see this happen. It's very unlikely. Yes. So if I say the statement, I mean, you hear a fair coin, but your brain rejects it. You reject the assumption. You said, no, it's not a fair coin. You understand? If somehow God tells you it's a fair coin, the probability is 1/2, but you just reject that it is a fair coin. And the same thing is with this experiment, right? If the probability of witnessing something is too low, then you don't believe the premise. You don't believe the premise is correct. And here the premise is that the fair coin here means that each person is equally likely to have for him to happen something. Let's, for instance, if you made the postulate that it's equally likely that men and women get breast cancer, then possibly this is a false postulate for some reason, right? So because you would see more women suffering from this disease rather than men, and vice versa. You have diseases that afflict men more frequently. Let's say color blindness. Color blindness is more frequently among men, right? So it's not equally likely that a person is colorblind if you know a person is woman or man, right? It influences the probability. So this is one way to sometimes see that it's something is not true, that the null hypothesis is not true. Good. All right, guys. So what else do we have? I mean, here I quote the theorem. If X is a binomial random variable with parameters NP and Y is a binomial with parameters MP, we used it implicitly in the previous example, then the conditional distribution of X, given that X plus Y is R, is hypergeometric with parameters N, M, and R. And by the way, I should mention that the distribution of X plus Y is going to be, if they're not counting the same things, over the same objects, over the same tiles, it's going to be a binomial with distribution N plus empty, right? Because it's like Y, if women and men are have the same probability of, they're like trials. One man, another man, and same for women. They're like different trials. So we have N plus M trials. If the probability of success in each category is the same, it's as if we just have more identical trials. It means that with respect to this experiment, there is no difference between men and women. Yes? Make sense? So theorem, if X is hypergeometric with parameters W, B, and N, that means this is what we want, this is what we don't want, and this is the sample size. And the total sum of let's say white balls and black balls goes to infinity in such a way that the ratio of white balls to total stays the same at P. Then the probability that X equal to K will be very close to the binomial probability, you understand? Which is natural. I mean, it's almost, this theorem almost doesn't require a proof. It means that if you have many balls altogether, let's say you have 5 million balls, let's say we have 6 million balls and 3 million of the balls are white, right? And you want to sample, let's say 5 balls, right? Then it's almost as if what you're doing is binomial distribution, because when you remove a white ball, you don't affect very much the amount of white balls that are still available. Yes, so it's almost independent. That's what I'm trying to say. Make sense? Yes, so then here in the proof, I'm going to carry a calculation of it. But in the proof, the calculation is better carried because look at it. We want n choose k, right? We want the probability that X equals to k, and we want it to relate it to n choose k, where n is the sample, right? So instead of using this natural way of doing it, I imagine that being labeled white or black is the random thing, but being sampled is not. So how can I get probability X equal to k? It means I took sample n and out of it k appeared white, and from things that I have not sampled, w plus b minus n, of them w minus k will be white. Make sense? So I just picked n, and k of them just suddenly turn and become white, and simultaneously there is like a connection with those I haven't picked. The rest of them turn white, so that in total I have w white, both. Yes. And then here in the denominator, w of the full of them, from the full population size, w will turn white. And then I just I have this thing. I then just isolate and choose k, and then I look at this number and this number, and I just simplify. So this number is the same as 1 over, so I can write w factorial b factorial w plus b factorial. That's this number here upside down, multiplied by this number, which is w plus b minus n factorial, w minus k factorial, b minus n plus k factorial. And here I can isolate them further. I can say w factorial over w minus k factorial. And here I have, you see, I bother w minus k here. Here I have b factorial over this part. And here I have what remains. It's this numerator divided by w plus b factorial. And then I simplify this. What is this? This I simplify by saying, well, what is it? It's w times all the way times w minus k plus 1. So I just divide by this number. Yes? And I do the same with b. Here I do that same thing with b. It's just b all the way to b minus this number plus 1. And now I erase this denominator. And then what do I do next? Then yeah. And then, of course, what else do I have? I have this remaining number, this one. I just yes, this number and this number I simplify, right? So you can see w plus b is bigger, so it will cancel this numerator, and w plus b, what do we have remaining? It's w plus b minus 1 over all the way to w plus b minus n plus 1. Yes? I just simplify all of them, right? So this is what I have as the ratio. And then what do? I take this number. So w over w plus b is the number p. So I take I divide this and this by w plus b. So it's this w plus b is gone, and here I get p. Now here I divide. I say I have w plus b. I divide this by w plus b and this by w plus b. What do I get here? Here I get w over w plus b minus 1 over w plus b, and w plus b is the total, is n. So it's p minus 1 over n. And what do I get here? I get 1 minus 1 over n, because I divide this by w plus b and I divide this by w plus b, yes? And I do that for the remaining ones, for all of them. I divide by just w plus b from the next one, right? And I get this, this expression. And that's the denominator. And then when I push n to infinity, what happens? Now, if n goes to infinity, we're assuming p is not bothered, not touched. This is going to 0. This is going to 0. Everything goes to 0. And here we have just 1, 1, 1. So the denominator is just equal to 1. And the numerator, how many p's do we have? We have all the way to, we have from 0 up to k minus 1 p's. So we have altogether p to the power of k here. And then how many 1 minus p? For b here, we would have 1 minus p, because b over w plus b is 1 minus p. So we have this thing is just from 0 to n minus k plus 1. So altogether n minus k 1 minus p's. So you get this expression. And that's exactly the binomial, which of course you could expect without doing the calculation. It's natural, right? It's, if you have a huge sample, then when you do the sequential removal, it's as if you haven't removed anything. So it's as if the next trial has the same probability. So if you have billions, right? If you have billions of balls altogether, let's say you have 8 billion balls and you have 1 billion of them are white, then and you have to remove, let's say, 10 balls, then it's pretty much not important that there is no replacement. You can tell it. Yeah. Good. So now we can move to geometric and negative binomial random variables. So let's begin with geometric. You see, so that's the confusing part. There is a negative binomial, which, you know, so hypergeometric and a negative binomial and onwards. So what do we have here? So geometric is this, guys. We will define geometric to mean we are going to perform a trial until we get a success. So we're gonna perform a sequence of independent trials, and we stop performing them once we get our first success. And X is the number of failures before the success. Yes. You have a different definition of geometric random variables. That's how it's defined in one book. In another books, it's defined differently. I just prefer this definition because I'm a pessimist. I prefer to look at the failures, right? You know this type of joke, right? A pessimist says that nothing can get worse. An optimist says, yes, it can. So here I look at the number of failures. So if you have k failures, that means we had k failures followed by one success. That's the probability. Good. Now let's sum them up. We could have 0 up to infinity failures. What do we get? We clearly get a geometric series, and it adds up to 1, as you can see. Right? This adds up to 1 over 1 minus p times p, so that ends up to be equal to 1. So everything works well. Then let's consider what is the cumulative distribution. What's the probability that we get X or less trials, or in other words, X or less failures before the first success? Yes. So how do we do that? Well, it is going to be this number. It's going to be 1 minus p. That's the probability of failure. Floor of X plus 1. If X is bigger than 0, and 0 if X is less than 0. Now, why is that the cumulative distribution? Very simply, what's the probability that we have? Probability of X being less than or equal to X is obviously the same as the probability that X is less than the integer immediately below X. You agree? Because I cannot have, let's say, 5.5 failures. If X is 5.5, then I'm asking what's the probability of having less than 5 failures or equal to 5 failures, right? So what is this? This is the same as 1 minus the probability that X is bigger than this floor, which is the same as 1 minus the probability that X is this is slightly bigger, so that means bigger than or equal to floor plus 1. And that means 1 minus the probability that absolute value of X, so floor of X plus 1 failures at least, right? Failures at least, and that's easy to calculate as 1 minus this number. So you can do that also with series. You see, with the idea of this calculation, it avoided doing series. That's all. But you could easily do that with series. Yes. So I just manipulate it, and I just what do I get? This means that I have at least this many failures, right? And to have at least this many failures, it means that this is the number. It's first. It means just first floor x plus 1 are failures. And then I have 1 minus that, yes? Think about it. Now let us calculate the expected value. We did it already many times. In this case, it's not useful to break it into any parts. We're just going to calculate it directly. What is the expected value? It is what? The expected value, first of all, I just make this calculation to just remind you that how do I sum up this altered geometric series where you have k times x to the power of k, right? You know how to sum x to the power of 1 plus x to the power of 2 and onwards. But what do you do if you have 0 times x to the 0 plus 1 times x to the 1 plus 2 times x to the 2? How do you add that up? And you can do that by, we did it several times already. You see, what I do is I split it into two series. This one is the one I know. So you see, it's k minus 1 plus 1 and the 1 factors to this series. And this series I know how to calculate, and this one looks very much like what I already solved before. Yes, this one looks like, this part looks like x over 1 minus x. Whereas this part, it is, if I just reparameterize it, you see, I can just factor out the x. And what I see over here is just x times the original e. So it's x times e plus this number. And in particular, e equals to x over 1 minus x squared. So that's one way to do this. Right? So if you are stuck on it after class, I can again carry it slower. We did it a few times. Are you following, guys? You know how to do this, right? Yeah. You understand the idea, right? Maybe. Well, let's be honest. You want me to do it slower, or is it going to be useful to you if I do it slower or not? But quickly, guys, come on, don't fall asleep yet. You have just another 7 minutes, then you can fall asleep. So, okay, Gustavo, since you're writing, I believe you speak for more people. I trust you. Here is the idea. Yes. Okay, guys, so what is this series? I call this E. Just for simplicity, what is this? This is 0 times x to the 0 plus 1 times x to the 1 plus 2 times x to the 2 and so forth. Agreed? Yes, that's what it means. Now, how do I calculate it cleverly so that I don't have to do a lot of calculations? All you have to do is remember this is a sum, right? So what I can do with it, I can write it. I mean, I can ignore the 0, right? I can say it's E equal to, you agree that if I started with k equal to 1, nothing is changed, correct? Because the 0 term, I mean, just I'm adding 0. Yes. Next, what do I do next? Next, instead of, you see, I want to break it up and look at what I already know to do from before. So what I do is I say, okay, this is k minus 1 plus 1 x to the power of k. Do you agree I haven't changed anything? Yes, I just rolled the same thing as before. Now, why did I do that? Because I can multiply the x to the k to both parts. And what do I obtain? I obtain summation k equal 1 to infinity k minus 1 x to the k plus x to the k. Do you agree? Now, what am I truly asked to do, guys? There are technicalities, of course, infinite series of when the sequence is a sum of terms, I cannot always just sum the terms separately, but each But if each part is convergent, you see, I have two infinite series, right? You know this theorem, right? So you have this theorem. If you have an plus bn, that's the same thing as n equal 1 to infinity an plus n equal 1 to infinity bn, provided each converges. Each component series converges. You agree? It's a result from Calc 2. If the sum of an exists and the sum of bn exists, I can break it apart. So doing that allows me to break this series. So I can say that this summation is equal to this summation. All right, guys, do you see that the second series adds up to x over 1 minus x? Do you see that, or do I need to explain that again? Right, remember that we did it at the beginning of the semester. This part is what? So look at this expression. So let's look at this first series. If I factor on x, this is k1 to infinity, k minus 1, x, k minus 1. And what do you see? K minus 1 is 0, k minus 1 is 1, k minus 1 is 2. And you see exactly the same pattern as you were seeing here, right? Initially, right? What is this? It's 0, x to the power of 0 plus 1, x to the power of 1. You see exactly the same pattern. Doesn't matter if it's written with as k minus 1. It doesn't matter at all. This is exactly the same pattern. Yes? It's 0 times x to the 0. It's 1 times x to the 1 and onwards, and you add them up, right? So this is the original series. And this other part, I know how to solve. I can do the same. I use the same idea to solve it separately. And it equals to what? It equals to x divided by 1 minus x. Yes. Now, what is this? So I have that e, the initial summation is just x multiplied by e plus x divided by 1 minus x. Yes. And so if I solve for e, I just move it. It's 1 minus x times e. So this is now 1 minus x times e equal to x over 1 minus x. And so e equals to x divided by 1 minus x squared. Good. So review your series, guys. It's very easy to sum up geometric series. So I hope you remember how to sum geometric series, and not necessarily the way you did it in calculus. You can do it the quick and dirty way, right? By just remember the way I introduced it. If you want some money, right? Like 2 plus etc., right? So it's that you can use that idea to sum every convergent geometric series. If you use that idea, we'll sum correctly to a normal number. So here is what we have. Here is what we have. The expected value of x is then what? Expected value of x. I use this formula. It's look at it. It's this is the previous number, right, that I have. So what do I get here? I get this is 1 minus p divided by 1 minus p squared. So it's this thing. You see x 1 minus x. If x is 1 minus p, then 1 minus x is p, and I square it here. You see, if x is p, 1 minus x, if x is 1 minus p, I'm sorry, then x, so then 1 minus x is p. It's confusing to say that, but you see it, right? You see how I apply it. And then all I need to do is multiply it by p. So what do you get? You get 1 minus p divided by p is the expected value. Good. And let me finish just the, should I finish it? Yeah, let me just finish up to here, please. And you can do the same idea for calculating the expected value of x squared. This time you have k squared multiplied by 1 minus p to the k times p. And what can I do? I can just, again, I have k minus 1 plus 1 squared, and I create terms where you have the previous power. It's like the one we solved, the expected value power, the geometric with the integer, and the geometric with the integer square again. So that becomes 1 minus, so when you simplify it, it becomes 1 minus p expected value x squared plus 2 times 1 minus p expected value of x plus 1 minus p. When you simplify it all, this is what you get. That you should try on your own, right? See, guys, if you can apply this idea to figure out what is 1 squared times x to the 1 plus 2 squared times x to the 2 and onwards, right? You can recursively figure other values as well. And so what is the variance? The variance is this number minus the previous number squared. Here it is. You see, we simplified it all, and then we get this expression. And the result is 1 minus p to the p squared. Okay, now when you have a chance, calculate it. And thank you for being patient and letting me talk for another 3 minutes. I imagine you're tired. So goodbye. If you don't have any questions, if you do, stay with me. I will stop recording.